Okay, let's go ahead and get started. Our next speaker, Mike Ossmann. I was at ShmooCon earlier this year. I've seen his presentation. I thought, oh, this is totally cool. This is something I would love to bring to the Dayton, Ohio area. Researchers like this that do this type of work are just hard to get your hands on. Not only that, he's a great presenter, and his method for presenting is excellent, and it's always fun. So I contacted him here, about 3 months ago. It was like stab in the dark. Let's see if we can get him in. Sure enough, he was excited to come to Dayton, Ohio. I'm not quite sure why.
Ignorance is bliss.
And actually, I had no photos of him doing anything he shouldn't have done, so it wasn't like I could blackmail him or anything. So, Michael Ossmann is a wireless communications security researcher who has been obsessed with Bluetooth for the past 3 years. Michael often gives presentations and teaches workshops at hacker conferences such as ShmooCon, DEF CON, TourCon. Michael founded Great Scott Gadgets in an effort to put exciting new tools in the hands of innovative people. Let's go ahead and welcome Michael.
Thank you, everybody. Thank you, Daryl. And thanks to Ohio Information Security Forum. It's really a pleasure to be here. So I amended my title a little bit for those of you who know Travis Goodspeed and his work. I've changed my title in his honor. At ShmooCon 5, 2.5 years ago, Dominic Spill and I gave a presentation called Building an All-Channel Bluetooth Monitor. And I stood up in front of everybody and I said sniffing Bluetooth is hard. And we went on to explain the success that we had with GNU Radio and the USRP, and I think we had some really interesting results. But admittedly, the solutions that we presented were somewhat kludgy, and they required a hardware investment of $1,000 or more. As one person pointed out to us later, at the beginning of our talk, sniffing Bluetooth was hard, and at the end of our talk, sniffing Bluetooth was hard. So I set out to make Bluetooth sniffing easy. And this is the story of that effort. And we'll talk a little bit about Bluetooth and why sniffing is hard. We'll talk about Ubertooth 1, which is the latest fruit of my labor, and we'll do a little demo and talk about its capabilities. Mostly today, I'm telling the story of how I got from there to here, and hopefully along the way we'll learn some things that will help you if you are interested in building your own Ubertooth 1, or if you're interested in other electronic devices that you might want to dream up. So why is Bluetooth sniffing so hard? A more specific question you might be wondering, and that I've certainly wondered over the years, is why don't off-the-shelf Bluetooth adapters support monitor mode? How many of you have ever used a Wi-Fi adapter in monitor mode? Okay, at least half the people in the room. So if you've used Kismet, if you've used Aircrack NG, AirDump, all kinds of different tools that are prevalent in the information security community that are very useful for working with Wi-Fi, use off-the-shelf Bluetooth adapters and put them into a monitor mode that allows them to just sniff any traffic that's going over the air. Why can't we do the same exact thing with Bluetooth? Well, there are some technical characteristics of Bluetooth that make this difficult, if not impossible. And one of these is that Bluetooth is a frequency hopping system. Each Bluetooth device may be transmitting on one frequency one moment, another frequency another moment. Different devices are transmitting at different frequencies at different times. And if you're just sniffing without any prior knowledge of the hopping sequence, you have a very low probability of capturing any one particular packet. A more severe problem has to do with the Bluetooth packet format itself. A Bluetooth packet starts with a very short preamble of only 4 bits of alternating ones and zeros. And then the first recognizable part of the packet is an access code. And this access code is derived from the LAP, the lower address part of the Bluetooth device address. So one device uses its own LAP, or the LAP of the device, or the master device of its little PicoNet, which is a group of 2 or more Bluetooth devices talking to each other. That device uses that LAP as the access code at the beginning of its packet that it transmits. And so normally, if you have an off-the-shelf Bluetooth dongle and it's joined that PicoNet, basically what you've done is you've programmed it temporarily to look for that particular LAP, that particular address. And a packet comes along over the air, and the Bluetooth dongle that's receiving looks for that access code, looks for that address, and when it sees it, it says, aha, I have a packet, and it processes it. But what happens if another Bluetooth device, a foreign PicoNet, something with a different address, transmits, and this dongle that you're using receives it? Well, it has a different access code, and so it doesn't actually even recognize that a packet existed at all. It's completely blind to packets that have different addresses. And this pattern matching, this correlation, is implemented in every case that I know of in silicon. So there's no way to get in front of it. There's no way to get between the antenna and the correlator and sniff promiscuously, sniff arbitrary devices with arbitrary addresses. And a third problem that makes, or a challenge, a characteristic of Bluetooth that makes it difficult to sniff, is that packets are whitened or scrambled by XORing the data to be transmitted with a pseudo-random sequence. And this is done for RF and electronic reasons more than it is for security. But still, it makes it considerably more difficult for a naive observer to decode an arbitrary Bluetooth packet. Now, all of these problems have solutions. And Dominic and I at ShmooCon 5 talk a lot about what those solutions are and how they could be implemented, both in theory and in practice. But the bottom line is they're complicated solutions. They're expensive solutions compared to the cost of implementing normal Bluetooth operation in a consumer product. The cost of implementing these solutions to these problems is very high. And so it's very unlikely that a consumer Bluetooth product would be engineered with those solutions in mind. And I think that a Bluetooth adapter must be engineered specifically for passive monitoring to meet those particular challenges and overcome them. These things have to be considered at the time of product development. And it's very unlikely that a consumer product will ever be developed with those things in mind. So, shortly thereafter, this was a little more than 2 years ago, I was thinking about the different solutions that we had at that point. And I like to think of Bluetooth sniffing solutions on kind of a graph where some solutions can monitor just one target PicoNet, for example. Other solutions could monitor many targets or all the targets in an area. Some solutions are capable of monitoring just one packet, just some of the packets that are transmitted by a target, where other solutions could potentially receive all of the packets transmitted by a target. And so what are the different, I kind of think of it in 4 different quadrants here. You could get an off-the-shelf Bluetooth adapter for as little as about $10. And you can do some limited sniffing, but generally speaking, you're limited to finding devices, target devices that are discoverable, right? You guys are all familiar with discoverability, like you can go into your Bluetooth device and switch it. You can turn on Bluetooth, turn off Bluetooth, but you could also turn on or off discoverability, right? Off-the-shelf dongles, generally speaking, can't do much with non-discoverable devices. So that quadrant isn't very interesting to me. But you could get a commercial Bluetooth sniffing device, and these are typically sold to engineers who are developing Bluetooth products. You can get a commercial Bluetooth sniffing device for about $10,000 or so that allows you to monitor one PicoNet or one target and capture all of the packets transmitted by that target. Okay, so that's an interesting solution, but it's pretty pricey. You can also get something. There's one particular product I know that's I listed $20,000 because when I first heard about it, that's what I heard the price is. But I've since heard it's closer to $40,000. That actually allows you to capture all of the packets on all of the targets, every Bluetooth packet on any channel, any PicoNet in the vicinity, capture them all. And so that's pretty interesting. Well, and then the work that Dominic and I did a couple of years ago with GNU Radio and the USRP, that allowed us to get into this category down here with a $1,000 platform, where we were able to, what we did was just sit on one channel. All of the Bluetooth devices around us are hopping through 79 channels, but we just sit on one and pick up every single packet that would be transmitted on that channel. And so that allowed us to pick up some of the packets from all of the targets in the area. That's kind of cool. That allows us to do a kind of a survey, Kismet style, what Bluetooth devices are in the area. And they're hopping 1,600 times per second. So only getting 1/79th of the packets really isn't that big a limitation. It doesn't take long before any target in your vicinity is going to hop through the channel that you're on, and you'll find out some information about it. Well, that was pretty interesting. And we also figured out how to use a slightly more expensive platform for about $2,000 to get into these other two quadrants. We were actually able to kind of implement frequency hopping, derive the frequency hopping system. We could sit on one channel for a little while, learn enough about the targets in our vicinity to be able to predict their frequency hopping sequence, and then get into that upper left-hand quadrant where we could capture all of the packets from one target. Or we had kind of a kludgy solution to actually get into the upper right-hand quadrant, which was pretty cool, and capture all the packets from all of the targets. Now, looking toward the future at this point, here I was 2 years ago thinking, this is great. We've brought some of these solutions into the realm of affordability, but it sure would be nice if we had a solution that like everybody could afford. And so I was looking at the lower left quadrant, not very interesting. Looking at the upper right quadrant, thinking, well, we're probably not going to get a solution in that quadrant for a whole lot less cost. But what about these other two quadrants? What about, shouldn't it be possible to make a lower cost device that can just sit on one channel, this is the lower right quadrant, sit on one channel, capture some of the packets from all PicoNets? Shouldn't it be possible to have a low cost device that can hop along? Maybe it only supports one channel at a time, but it could hop along with the target PicoNet and capture all of the packets from one target. That should be possible, and I thought it should be possible for somewhere around $100. Right? This was kind of the price point at which Wi-Fi adapters, like in the golden age of Wi-Fi hacking, when AirSnort first came out, and people were like, wow, we can monitor these things, and we can, crack web and so forth. In that time period, I think Wi-Fi adapters that supported monitor mode were in the $100 price range. So I thought, if we can get to that low of a price, then it should be something that everybody would be able to have in their toolkit. And so I established a goal. I wanted to make a Bluetooth sniffing platform that's open source. Anybody should be able to build one of these things. I want it to be widely available. Anybody should be able to acquire one. I wanted it to be portable, because we're working with portable technology. And I wanted it to be somewhere around the $100 price range. So I didn't know much about electronics at the time. But I knew a fair bit about software-defined radio. And so I thought, well, maybe I can build some kind of a special purpose software radio receiver peripheral for a computer. I was familiar with the USRP, which is a more general purpose and more expensive software radio peripheral. I thought maybe I could make kind of a stripped down version, something smaller. It would have an antenna and some kind of an RF front end that would down convert a signal from 2.4 gigahertz down to a baseband that could be sampled with some kind of an analog to digital converter, and then it would stuff the raw samples over USB or some kind of an interface into a PC where we could run the GR Bluetooth software, the GNU Radio Bluetooth software that Dominic and I had worked on. So, and I thought, maybe this could be affordable if I could take some of these, maybe rip these components out of consumer devices somehow. So I looked at RF front ends, and I ripped apart a lot of things. Phones, baby monitors, video senders. There are all sorts of interesting products that operate in the 2.4 gigahertz band. And I kept running into the same problem, that their wireless receivers or their wireless transceivers were highly integrated ICs. And they were like all the analog and the digital components would be integrated in one chip. And so I couldn't insert myself in between, into that baseband layer where I wanted to be. It's basically the exact same problem I had looking at off-the-shelf Bluetooth products and chips that are made for off-the-shelf Bluetooth products. I couldn't get into that intermediate layer that was in there in the silicon somewhere. So I started to get the idea that maybe I'd have to kind of roll my own front end somehow. And then I was looking at the ADC section of this solution, and I was looking at all sorts of products, consumer products that have ADCs, the analog to digital converters, and in particular I looked at cable, like TV tuner cards. Some of these are somewhat hackable, and the most hackable ones I looked at were in a PCI form factor. Well, that wouldn't be super portable, right? I really wanted something that I could plug into my laptop and carry with me, on a wireless assessment or something. And that wasn't very attractive, and so I started to get the idea. There are some USB TV tuner products that are probably worth further study here, but I was starting to get the idea that I might have to roll my own back end too. And this was only a little bit terrifying. Some of you probably recognize this as Ohm's law, right? Yeah. It's a really important thing to know if you're working with electronics. And it really nicely sums up everything I knew about electronics at the time. So, I can learn though. I started learning more and more about electronics and talking to smart people and reading a lot of data sheets. I mean, data sheet after data sheet after data sheet. And if you've ever looked at doing any electronics of your own, you know that you spend a lot of time reading data sheets. These are the documentation for the components that you might use in your electronic circuit. If you're going to put something together out of these parts, you have to RTFM, and DFM is a data sheet. And frankly, I didn't really understand these data sheets at first. And it took me a long time of learning about electronics and putting things together and making smoke and stumbling through a lot of acquired knowledge before these things really started making more sense to me. But it didn't take me too long to figure out that kind of an ideal that I have to build my device around some kind of a microcontroller, a small microprocessor, and I had this ideal solution that sort of emerged. There were some microcontrollers that have built-in ADCs. Well, if I could find one that's fast enough for Bluetooth signals, it might be nice to have that integrated into my microcontroller. There are some microcontrollers that have integrated USB interfaces. Well, if I can find one that's fast enough, again, I needed high-speed USB, not low-speed or full-speed USB, because of the bit rate required for this raw radio waveform that I wanted to send over the USB to the PC. So, but finding a microcontroller that has both these things, both fast enough for my solution, was looking pretty difficult. And but I did find out that Atmel was coming out with this SAM3U microcontroller, ARM microcontroller that looked interesting, like it, at least it might come close. And so I ordered a development board, and then I headed up to tour camp. And did anybody here go to tour camp? Anybody? No? Oh, too bad. Hopefully there will be another one someday. It was a really good time, and What was great for me about tour camp was all of the interesting people that I met, and some of whom figure into the story. And good times were had at tour camp. Some of the people that I met there, I met Travis Goodspeed, who I mentioned earlier, and he ended up helping out with this project a little bit here and there. I also met Jared Boone, who is an open source hardware developer, who had organized the Dorkbot PDX camp. Now, Dorkbot is a global collective of artists and hackers, or people who do strange things with electricity. And the Dorkbot PDX group is the Portland chapter of Dorkbot. And so Jared and a bunch of guys from Dorkbot had come to tour camp and put this, it was sort of organized into sub-camps. And so I ended up camping with the Dorkbot PDX guys and getting to know them. And so Jared ended up also kind of becoming my mentor in all things electronic, and he figures into this story later on. So I got back from tour camp, and my SAM3U development board came in the mail. Yay! And then I started working with it. Oh no! There were a bunch of problems. The first problem I had was really just a problem of my misunderstanding the datasheet. And Jared told me that this would be the case, but I had to prove it to myself. That although the datasheet says it has 8-channel ADC that operates at 1 million samples per second, that doesn't mean you can operate all 8 channels at 1 million samples per second, right? You can take a maximum of 1 million samples per second, and any one of those samples can come from any of those 8 inputs, right? You don't actually have 8 ADCs. So that was my own problem. But then I had another problem, is that you didn't actually get 1 million samples per second, even though all of the documentation for this part said you could get 1 million samples per second. And so I worked with Atmel support on this issue. I couldn't get more than about 800 kilosamples. And finally they said, yeah, that's all you're going to get. They said, oh, the ADC works just fine at 1 million samples per second. We just can't deliver them to the CPU fast enough. And to me, if the documentation had said 1 microsecond conversion time, and then there were some hidden extra delays in there or something like that, well, I could kind of live with that. But if you're going to say 1 million samples per second, it would really be nice to actually be able to get 1 million samples in 1 second. And but I learned a lot from this. And one thing that I learned here was that if you look at a data sheet for a component and you see some maximum limit and you want to run at that limit, you are likely to run into problems, no matter what that limit is. So another problem with this particular part was availability. I got the development board in the summer of 2009. Well, in March 2010, I said to myself, I wonder if I can buy any of these chips yet. No, 17-week lead time on those. So I actually put a note in my calendar, and I looked 17 weeks later, 26 weeks. So I looked a few months after that, and it said manufacturing delays have been reported on this product. No kidding. Yeah. So this is like 2 years now after I originally looked at it, and these parts are finally starting to become available. But I learned a lot, and I was also learning at the same time, while I was looking at what kind of microcontroller I might use and the ADC part of the solution, I was also looking at the RF front end part of the solution, and looking at a lot of the ICs, the integrated circuits that were shipping with, or starting to ship, or becoming available for new products like WiMAX products, LTE products, new TV tuner chips. Some of this stuff was starting to look really interesting, and mostly the solutions that looked most optimal for my application were the ones that were new and weren't really publicly available. You couldn't just go to DigiKey and order 10 of them. And so I was thinking, well, how am I going to figure out what products, which of these parts might work in my product, and how could I put them, get the documentation for them, maybe get some sample parts ahead of when they become widely available. And I'm just some schmuck who's just doing this as a hobby, trying to make some kind of a solution. So I decided to put this fake company together. I registered at greyscottgadgets.com, and I drew this little logo, and I put up a website, and I started sending people emails at different manufacturers, and getting on the phone and trying to get a hold of documentation and sample parts and stuff, and it didn't work at all. I think the net result of this effort was one piece of documentation and 0 sample parts. But what if it had worked? What if what if I had actually got some good documentation, and one of these manufacturers of these parts sent me some samples, and I said, hey, this is going to work in my Bluetooth sniffer. And maybe they'd require me to sign an NDA before I could get a hold of the documentation. What good would that do me for my goal of making an open source solution, right? That anybody can build. So it finally dawned on me, after months and months of this, that I needed to establish some requirements for the components that I use in my solution. And one of those is that the parts must be available. And these parts should be available in single quantity. So if somebody wants to build just one Bluetooth sniffer, they should be able to do that. And the parts should have some publicly available documentation that you can get to without having to sign a non-disclosure agreement. This is all stuff that probably should have occurred to me on day one, but it took me like a year to get to this point. And meanwhile, during this year, I was learning more about electronics, and I was working on various microcontroller projects, most of which I don't even have photos of. I was learning how to work with small microcontrollers and how to write code for them. I was a software guy, not a hardware guy, so I was learning how to do this stuff. And one that I do have a photo of is a spectrum analyzer application I wrote for the Girl Tech IME, because it's so cool and so connected. And this is just a little toy, text messaging toy, that has a 900 megahertz radio transceiver built into it. It's actually an integrated circuit that has both a microcontroller and RF transceiver integrated in one package, which is kind of cool. And I was introduced to the IME by Travis Goodspeed at ShmooCon 2010, which was the one where there was the big snowstorm. And some of you were nodding your heads who were there. And Travis and I spent a lot of time hacking on these things in the hotel bar that year. Thanks to Travis, I got involved in working on the IME, and he kind of encouraged me to look at the IC that was in this product and the other ICs in the family, in particular the CC2400. Now, it turned out that I had looked at the CC2400 before. I went back and I found notes that I had made months before from the data sheet, because it's an interesting part for Bluetooth sniffing potentially. It's a wireless transceiver, so actually it could potentially be used for transmitting or receiving Bluetooth packets. It operates in the 2.4 gigahertz band. That's where Bluetooth operates. It supports a modulation of 1 megabit per second Gaussian frequency shift keying, which is the same modulation that Bluetooth uses. And here's the kicker. Here's the thing that I overlooked the first time I had looked at this part. It supports what they call an unbuffered mode. So usually, when you hook up this IC to a microcontroller, it gives you this serial interface where you can talk to the transceiver IC, and you can say, transmit a packet that looks like such and such, or receive a packet but look for such and such characteristics in it. But it has this packet format that it supports. And this packet format was not compatible with Bluetooth. And this is why I overlooked it the first time around, because I said, well, I can't mangle this packet format in such a way that it would actually promiscuously sniff Bluetooth. But there's this unbuffered mode, and what that is a second serial interface. that allows you to tell the transceiver to tune to a specific frequency, activate its demodulator, and start streaming bits non-stop out this serial interface, completely bypassing the packet handling capabilities on the chip. And there are some other products on the market that have similar capabilities. They call them like direct mode or some other things. But what TI calls it is unbuffered mode. And it turned out that I could use this chip that looked like to do promiscuous Bluetooth sniffing, just by bypassing its packet handling completely and taking care of that myself, which was, I was already doing with software radio. Anyway, so I developed, a couple weeks later, after ShmooCon, I was snowed in another snowstorm in Boulder, and I sat down and kind of drew out the Ubertooth architecture for the first time. And this is basically the same architecture I have today. It's an antenna connected to a CC2400 wireless transceiver IC connected to a microcontroller with full-speed USB interface to a PC. I didn't need high-speed USB anymore because I'm not dealing with raw radio waveforms that are digitized. I'm dealing with 1 million bits per second. So that actually reduced the requirements of my microcontroller down to gave me a lot of options. And so Jared Boone, who I mentioned earlier from Dorkbot PDX, he was kind enough to design and lay out a little breakout board for me that I could assemble, put the CC2400 on, and talk to it. I first talked to it with a GoodFET, which is a board that was made by Travis Goodspeed, and then Jared had this board manufactured through the Dorkbot PDX PCB order. This is a kind of a group order run by a guy named Lane in Portland. People who, anywhere in the world, can send him their small designs for electronics printed circuit boards, and he panelizes them all together into a bigger panel that he can get manufactured at a low cost. And so it's a kind of a shared cost system that allows people like me to throw in an order for a small, like I can get 3 small boards for a few bucks instead of having to buy much bigger boards or spend a lot more. It's great for prototyping. So I then, after connecting this breakout board to the GoodFET, I tried connecting it to other microcontrollers, tried some things out, and I finally found this LPC 1700 series of microcontrollers from NXP that I liked for this application, and I got a breakout or a development board, like a commercially produced development board for that microcontroller series, connected it to my breakout board, and this was like the first working prototype where I actually decoded, like streamed bits over to a PC and decoded a Bluetooth packet for the first time. And so then I didn't touch anything. I think this is still sitting on my desk, gathering dust, so all the wires are still in place. And based on that success, I designed Ubertooth 0, which was the first board in my series. And I had this ready for TourCon last fall, where I gave a short little preview talk. It has the LPC 1700 microcontroller, that's the big chip on there, and then the smaller chip is the CT2400. And it worked. And then, but I always knew that this was kind of a stepping stone. I wanted to build Ubertooth 1. That was kind of the product that I had in mind. This was just sort of a trial run to see if I can get the basics working. And I wanted to get Ubertooth 1 working for ShmooCon, which was like 2 or 3 months later, about 3 months later. And, due to a variety of problems, I ended up being delayed for this reason or that reason. I had an error in a board that I had manufactured, and there were manufacturing delays, and I was delayed due to my own injuries. And a word of advice, if you ever see a car starting to roll down a hill without a driver, and you think to yourself, I could chase down that car, jump in, and stop it. Just don't. So anyway, for a variety of reasons, I didn't get this board done. Finally, it was like 2 days before ShmooCon, and I finally got Ubertooth 1 working. So I brought it to ShmooCon, I showed it off, and the main thing that was different in Ubertooth 1 versus Ubertooth 0 the main functional thing was that I added the CC2591 RF front end, which is just an amplifier. It improves both the transmit power and the receive sensitivity. So it's actually it meets the specifications for a Class 1 Bluetooth device, which are the longer range ones. And actually, it exceeds the specifications of any Class 1 device that I've actually looked at. But one problem I had with getting the CC2591 working is that the reference design for this chip required a 4-layer circuit board. And I tried some things, wasted some time trying to make it work in 2 layers, but that's really tricky and would require a lot of extra testing and expensive test equipment and stuff. And it was easier just to copy those really sensitive parts of the design directly from the reference design and do it in 4 layers. Well, I had designed Ubertooth 0 in Eagle CAD, which those of you who have done any hobbyist electronic stuff, you might be familiar with Eagle CAD. It's pretty useful software, but it's crippleware. And you can download a free version that lets you do 2-layer circuit boards. But if you want to do 4-layer circuit boards, you have to pay. And it's not that expensive. I really personally would have been happy to pay it and just use it. But then it occurred to me, why should I require? Why would I want to put out an open source product, open source hardware? Theoretically, people should be able to take it, modify it, build their own variations on it. I shouldn't require that those people pay for this software to be able to do that if I can possibly avoid it. And so I tried out KiCad, which is a fully open source electronic design automation package, and it turned out to meet my needs just great. And so I'm really glad I did. I'm using KiCad for all my projects now, and if you're into electronics, I highly recommend you check it out. And so I designed Ubertooth 1 in 4 layers, and it ended up looking like this. It's a little smaller than the Ubertooth 0. It has an external antenna connector, a CC2591 RF front end, the CC2400 wireless transceiver IC, LPC 1700 microcontroller, which is an ARM Cortex M3. It has an integrated full-speed USB interface, and so I was able to just make this little USB dongle that you can stick an antenna on and sniff Bluetooth. And the microcontroller could be any of these from the LPC 175X family, theoretically. I've sort of established a design minimum of the LPC 1754, and the main difference between all of these is just the amount of storage they have, the amount of program, flash memory, and RAM. I have donated a board to this afternoon's raffle, and so that one has the LPC 1759 on it. And let me, what, it's disappeared already? So I'm gonna do a little demonstration. This is like the simplest demo I've ever done. Sounds like famous last words, right? So I'm just gonna plug in the Ubertooth 1 and type Kismet. There we go. So, how many of you have used Kismet before? A few of you? Okay, quite a few. So, basically, the newer versions of Kismet, what's been out for the last year or so, supports this plug-in architecture. And it just allowed me to just develop a plug-in for Kismet that talks to the Ubertooth. And you can see it's generating a list. I'm standing in front of the screen. It's generating a list. So far, it's only found one Bluetooth device address in the room. Oh, hey, there's another one. There's some more. So, and actually, that last one, which was the last one listed, was the first one it detected. That's actually a special device address that ends in 98B33. That's the general inquiry lower address part. So when you tell your Bluetooth device to find new devices, it sends out a whole bunch of packets with that particular address. So that's not like a real singular unique device. That's an address that's shared by all devices when they do those inquiries. And you'll notice that I'm only getting part of the address. Remember I said that lower address part of the address is transmitted with every packet as a part of the header. And that's the last 3 bytes of the Bluetooth device address. And that's why I always get those last 3 bytes. Sometimes we're able to fill in that third byte. You see how those top 2 there have a third byte filled in? We learn that over time. And so those particular piconets that have those 2 addresses at the top there are devices in this room that we've heard from a few times. And over a small number of packets, we've deduced what that UAP, the upper address part, is. And then the first 2 bytes it's called the NAP, the non-significant address part. It's called non-significant because you don't really need it for much. And if you wanted to use this to survey a bunch of devices in an area and then go and attack them and see what are these devices, go talk to them, find out what kind of devices they are, figure out if you wanted to do some kind of a security assessment against those devices. You don't actually need the NAP at all. You can just skip those first 2 bytes. You can just make up whatever values you want there and connect to those devices. So really all you need is the LAP, which is the 3 bytes on the right, and then the UAP to be filled in which you get over time as we observe more and more packets. And let's look at a couple other things too, because the board can be used, potentially for more than just Bluetooth, which is kind of cool. One thing that was an easy thing to implement was a spectrum analysis function. And so this is a little spectrum analysis tool that was written by Jared Boone that I mentioned earlier. And this is just showing the 2.4 gigahertz ISM band and the activities around in this room. And there's also another, we actually have, I don't think anyone's actually seen this one yet, but Draghorn, Mike Kershaw, who wrote and maintains Kismet, he also has a little software tool called Spec Tools that was designed to work with the YSpy, which is a commercial, low-cost, 2.4 gigahertz spectrum analyzer. So he retrofitted his Spec Tools to know how to talk to an Ubertooth. And so this is just a different, a little bit more sophisticated spectrum analysis function. And it lets you see some things like you can highlight, now I'm highlighting Wi-Fi channel 1. Aha! So you can really kind of see trends. And if I were to say go to my mobile phone and turn on Bluetooth, which I don't do very often, and if I were to run like a close range, an inquiry scan, you should see in the top, you see those red dots showing up? Can you guys see them from back there? Yeah. Those are red because they're really high powered because I'm at close range here. So that's how I was able to differentiate them easily from other things in the room. And you can see the inquiry scan just ended. Right? The phone stops transmitting that whole bunch of packets. So, and potentially this could be used for some other things too. But so far, that's about all the software we have kind of working yet. Yeah?
The different, the random hopping that goes on, is that on a pre-created list of frequencies? Or
Yeah.
is it intended to be truly random?
It's not, is it intended to be truly random? No. It's intended to be pseudo-random with the primary characteristic of interference avoidance, right? It's a pseudo-random sequence that, and if you look at the sequence over time, you'll see that you won't get the same nearby channels 2 packets in a row. There's always a certain amount of spread between the channels in consecutive packets. So it's designed. The pseudo-random sequence is designed more for collision avoidance or interference reasons than it is for any other reason. It's not supposed to be like a cryptographically unpredictable sequence or anything like that. It's a pseudo-random sequence that's derived primarily from the Bluetooth device address. And so it is somewhat unique per piconet and based on the address. And if you look at my talk with Dominic 2 years ago, building an all-channel Bluetooth monitor, I talked more at length about how we're able to learn that sequence and predict it.
Can you tell the kind of device you're looking at based on the frequency hopping pattern?
Not real. Not based on the frequency hopping pattern. The pattern doesn't reveal anything more than the device, and the device address, and the device address reveals a pattern. So all you can really learn from passive monitoring, as far as identifying a device, is the address itself. Now the address is a MAC address, and so it has a manufacturer code, just like a Ethernet address, right? So you can learn a little bit about a device and find out what its manufacturer is, or at least what its likely manufacturer is, because you might be missing those first 2 bytes of the Bluetooth device address. But there aren't that many manufacturers of Bluetooth devices, right? And if they come out of the same list, it's the same list. Like if you look at the manufacturer IDs, that the lists that you can get online or that ship with Wireshark or Nmap or whatever, it's the same list, and it's just a subset of those that happen to manufacture a Bluetooth.
We're interfering.
The countdown to the end of my talk has just begun. Yes?
Or maybe the device goes beyond this device that actually goes to identify personal information or data?
Oh, the actual data. Right. Oh, you want actual data? Actually, the Kismet plugin, I was pointing out how that UAP, that third byte of the address, only gets filled in sometimes. Like when we've seen enough traffic to be able to deduce what that is. When that happens, as soon as that happens, Kismet starts dumping decoded packets into a PCAP file that can be read with I have a Wireshark plugin for decoding Bluetooth packets. So until when that UAP is not filled in, we don't actually know how to decode the packet. It's that whitening that I mentioned early on in the talk. We can't de-whiten a packet without figuring out what the UAP is. And so when we have learned the UAP, which usually only takes a handful of packets, then from then on, we can dump the complete data that's in those packets. And we are dumping it to a PCAP file, and you can analyze it with Wireshark. So that's it for my demonstration. I want to talk a little bit about surface mount technology. Yay! When I started this project, and I was getting into electronics, I saw some really impressive surface mount soldering work being done by people like Travis Goodspeed and Amanda Wozniak and the SmartPhone guys and Lady Ada, and I decided I wanted to have nothing to do with it. And over time, I finally realized that it would probably be a necessary evil, but eventually I learned to love it. And here's why. Surface mount parts are small, surface mount parts are cheap, and surface mount parts are fast. And by fast, I don't just mean they're fast to assemble, which they are if you do it right, but they operate with higher frequency electrical signals. They can do things that bigger, older parts with longer leads simply are physically limited. They cannot do. And so it allows you to do things like build a Bluetooth dongle that sniffs Bluetooth. It just would not be possible with through-hole parts. And it's not that expensive. They're not that expensive or difficult to work with if you do it like this. First of all, you must order PCBs. It's really kind of pointless to work with surface mount parts without actually building a circuit board to mount them on. That's what they're made for. People do all kinds of crazy things like dead bug wiring, QFNs, and stuff like this. when it's really not that hard to just design a circuit board and get it made. You can use KiCad, totally open source, free software package to lay out your board, and you can use the Layton's Dorkbot PDX group order that I mentioned earlier. And if you want to build an Ubertooth 1, he does 4-layer boards, 4-layer orders, not as frequently as he does 2-layer orders, but usually once a month or so he does a 4-layer order. You can get 3 of these Ubertooth 1 boards built for $18. Hey, what a deal. And so, second, you should have a solder stencil. There are other ways to apply solder to a board for surface mount soldering, but they're all terrible except for stenciling. You get some solder paste, you get a stencil. You can have these manufactured. This one is from a place called O'Hara RP, which is in Ohio. I can't remember where. But Ryan O'Hara is a good guy, and you can order these Kapton stencils. They're really durable for about $25, and they can be used multiple times. And you just get a putty knife or something like that, and a little solder paste, slap the stencil on the board, just slide it across, and peel off the stencil. And then all you have to do is place your components. And you can also, even though the Kapton stencil is only like $25 or $30, there are some potential ways to use lower cost materials for stencils. And Jared Boone has had some success just by throwing some Avery labels in a laser cutter. And this is kind of cool because you peel off the backing and the thing sticks to your board. Because one of the things that stenciling is fairly easy, but what it does take a little bit of practice to get the hang of keeping the stencil positioned on the board while you're applying solder. Well, this kind of takes that away because as soon as you have it placed, it's adhered to the board temporarily, and then after you apply the solder paste, you just peel it off. And his thinking was, why should I spend even $25 on a stencil when I can spend like $2 on a stencil that I'm only going to use once, right? It's cheaper to get 3 Avery label stencils than it is to get 1 Kapton stencil. Well, I've tried this and I had not as good success as Jared. I had a problem with the adhesive staying on the board. So it was a bit of a mess. It's something that is worth further study. And I actually have some that I haven't tried yet. I have a friend in Colorado who has a laser cutter, and we've tried a couple of different materials. I have some stencils for the Ubertooth 1 now that are made with Post-it craft paper, which is it's like a Post-it note, but it's a full sheet that has the adhesive over the whole backing. So it's that reusable adhesive stuff that isn't super strong. The Post-it craft paper is a little thicker than I had hoped it would be. It's like 6 or 7 mils thick, as opposed to a typical stencil, like those Kapton stencils are like 3 mils thick. So, but it's definitely worth trying. And then you just have to place the components, and you need a fine tip pair of tweezers. You can these are some tweezers that I got at Spark Fun. And this isn't as hard as it might look. Some of these components are extremely small, but the solder paste, you can kind of see some of those pads that are empty there have that grayish paste on them. It's a little bit sticky. It's not very sticky, but it's just enough that when you get a part in place, it stays there. Unless you catastrophically, sweep the board off your table accidentally or something like that. Those parts stay there as you place other parts, and you just kind of go cross-eyed for a while, and everything kind of starts to seem really big. And but eventually, you get all these things on the board, and you can just stick it on an electric skillet, heat it up, and solder the entire board all at once. You should get yourself one of these infrared thermometers. You don't really need them; they're just fun to play with. And so, thanks to being able to use these kind of techniques for home surface mount soldering, I was able to design and build this board small enough to fit into an off-the-shelf enclosure that you can buy. It doesn't show up real well there, but there's just a black plastic enclosure. And actually, the board that I donated to the raffle has an enclosure. What's that?
I said that's missing too.
Oh, the enclosure's missing too. But actually, even though it's designed to fit this enclosure that you can just buy for a couple bucks online, I actually prefer the one in the upper right there. Just has a sleeve of clear heat shrink tubing. Just stick a little heat shrink, like 5/8 inch heat shrink around it, heat it up, and that provides more than adequate protection without taking up much room, and it also allows you to see all the blinky LEDs, which are very handy, especially for development. So the total cost, did I actually meet my $100 goal? The bill of materials, the parts to be soldered on the board add up to about $40 in single quantity. And you can get 3 PCBs, as I mentioned, for $18. You can get a stencil for about $25. You can probably want an antenna on the thing. If you want, you can get an enclosure. It only costs about $3. So ignoring various shipping charges, ignoring spare parts that you'll probably need when you screw things up, ignoring some of the tools that you may need, but realize that a lot of them are pretty affordable, like an electric skillet and a pair of tweezers, right? But ignoring those kind of reusable things that you could use for a lot of projects, yes, you can build one of these for under $100, which was kind of my original goal. And it can do all these things. It can do monitoring of basic rate Bluetooth, and that's what I was showing today. It can also do spectrum monitoring down on the bottom there. I was also showing you that today. It can do potentially injection. We don't have code to do this yet, but the hardware is designed to have the capability to actually transmit Bluetooth packets. And that's something that I'm really working toward right now, is getting software to the point where we're able to do injection, because that's a capability, kind of a fundamental capability. Just like we've lacked adequate tools to do Bluetooth sniffing for all these years, we've also lacked tools for injection. I mean, it's been 10 years that Bluetooth has been on the market, right? And through all this time, we've never had an affordable tool that just did the basic function of monitor mode. And I think that as security professionals, we do ourselves, our employers, our clients, and the general public a disservice by ignoring Bluetooth vulnerabilities simply because we haven't had adequate tools, right? If somebody like me, who didn't know anything about electronics, could come along and in 2 years develop this thing, why didn't somebody else beat me to it? Somebody who actually knew what they were doing. How many of you guys saw the MS11053 vulnerability this week? Bluetooth, Windows 7, Windows Vista vulnerability. Well, this is the one critical vulnerability this last patch Tuesday from Microsoft, and it looks to be. I haven't actually seen an exploit, but it looks to be a remote code exploit done over the air via Bluetooth. And a lot of the talk about this patch, and the folks from Microsoft are saying, well, people, you'd have to be in discoverable mode for somebody to actually get your device address and be able to deploy an exploit onto your system. That's not true. This project demonstrates that you don't have to be in discoverable mode. A non-discoverable device is just as vulnerable to passive discovery of its Bluetooth device address as a discoverable device is. The only reason there's been this myth that discoverability or lack of discoverability protects you is because nobody's bothered to see if they can make a tool to do it. That's it. So potentially it could be used for some other things. The Ubertooth platform, like Bluetooth Low Energy, is a new specification that's kind of just hitting the streets now. There are some development boards available, but no real consumer products yet. But they should be coming in the next few months. And Ubertooth 1 should be able to sniff and eject those. Also, 802.11 FHSS. I don't know if you've ever seen presentations by Rob Havelt. He has done some interesting stuff. This is the older 802.11 technology that's still used in some industrial settings. Here's an example of some spectrum monitoring. That, like, the first thing I did was spectrum monitoring. And here's an example of some early work I've done on capturing some Bluetooth low energy packets. I don't have any kind of general purpose code for this, but this was just sort of a proof of concept to make sure that I could capture Bluetooth low energy packets. All in all, I think that this project has produced something that fits a really important niche. And so I really wanted to make this thing available to as many people as possible. And so, first of all, that means it absolutely has to be open source, right? That was kind of my requirement from day one. Anybody should be able to pick up my design, build it themselves, and I encourage people to do that. And I would love it if I'd see people, actually modify it, make their own modifications. But also, I know that a lot of people don't really want to do surface mount soldering if they don't have to. So I decided to see if I could kind of make some available for sale. And I said, well, I have this company. Why not pretend it was legit all along, and see if I can make some boards for people. So starting in basically the month of February, I had this pledge period on Kickstarter, which allows people to kind of pledge support for a project and to bring an idea fund an idea so they could be manufactured kind of thing. And mostly it's used for creative work, like artistic works, bands that want to put out an album, or a filmmaker who wants to make a documentary or whatever. But they also do technology projects. And so I threw up, Ubertooth 1 on Kickstarter, and I met my funding goal in 4 days. So it was funded, and I actually have Great Star Gadgets as a legitimate company now, and I've delivered all those boards to all the Kickstarter backers. And so if any of you back me on Kickstarter, thank you, because it's made this project a reality, not just for people who actually want to go through the trouble of soldering up their own boards, but it's made it a reality for other people who don't want to do the hardware hacking, but just want to get a hold of a tool that they can use to do, wireless. People do. How many of you guys have ever done a Wi-Fi security assessment? How many of you have ever done a Bluetooth assessment? Right. So people should be able, if you do Wi-Fi security assessment work, you should have the ability to do Bluetooth assessment work, and that's kind of the whole motivation for this project in the first place. So I want to say thank you to all you guys for having me. I want to say thank you to the Ohio Information Security Forum and Daryl for bringing me out here. I want to say thank you to all my Kickstarter backers, and in particular, I want to say thank you to these guys because they all had a significant role in my being able to develop this. In particular, Dominic Spill, who I mentioned a couple times, he did so much of the work with me on the GR Bluetooth project and kind of laying the groundwork to figure out that this stuff would be possible at all. So like a theoretical work. And I'm still using lots of his code. And he's writing code for the Ubertooth. And Jared Boone, who's really kind of my mentor in all things electronic, has really been a big help to me. And there's some related work that I recommend you guys check out. Killer Bee is an interesting project from Joshua Wright that takes sort of a similar approach, but he was able to find an off-the-shelf Zigbee development board, and that allows him to do the same kinds of things I'm doing with Ubertooth for Zigbee without having to actually design and build his own board. Kikiri Key is a wireless keyboard sniffer project from Torsten Schroeder and Max Mosier. And their original version targeted 27 megahertz wireless keyboards. V2, which you may or may not have heard of, targets 2.4 gigahertz wireless keyboards. And they actually had a lot of the same kinds of challenges that I did in sniffing those keyboards, which use a proprietary protocol that I had, the same challenges I had looking at Bluetooth. And the Next Hope badge that was designed by Travis Goodspeed, the badge for the conference last summer, he's published some interesting work just in the last few months. Like in February, he published an article on how to use the wireless transceiver that's on that board to do some promiscuous sniffing in kind of a kludgy way you can actually use it to do LAP sniffing of Bluetooth, for example, using his method and an even lower cost platform than the Ubertooth, which is really exciting. It's a little bit kludgy. It has a lower probability of success, so you have to see a lot more packets before you get the address, but it's capable. And so a lot of this stuff is really exciting to me. This is all open source software, and a lot of this is open source hardware, and it really makes me kind of hopeful for the future. As more of us in the information security community are exploring hardware, and more people who know about hardware are exploring security, we're kind of bridging this gap between expertise in software and hardware and security, and in the middle, where all these things converge, there's all this exciting work that is really giving me a lot of hope for the future. Because in the future, when a popular new technology for wireless communication emerges, we are not going to wait around for 10 years for somebody to build the tools that we need to do our jobs. We'll just build it ourselves. So thank you very much for having me.